Hi, I quickly just want to go over my Astrostats final project because I found it quite interesting. I took the liberty of trying to find out whether dark matter or modified Newtonian dynamics would explain rotation curve data better. Now, rotation curves have puzzled astronomers and astrophysicists alike for decades because they seem to completely contradict what we understand about dynamics and gravity. And there's been a few very prominent methods that have attempted to explain why this might be. The most popular is dark matter, which essentially argues that there's some matter that we just simply can't see. And another less popular one is modified Newtonian dynamics, which argues that simply our Newtonian model of gravity and dynamics is wrong, and there needs to be an adjustment to it, which comes out in this term called acritical, which is, as you'll see, something that we'll be fitting for. Now, to do some very simple testing, I took 8 galaxies from the Spark data catalog, and I started by doing preliminary linear least squares, nonlinear least squares parameter fitting, and I took the chi-squared of each model and galaxy, and I created this table. As you can see, generally, dark matter performs better, but we can't really make any massive conclusions based off of that because that's not exactly meaningful. We need to do something more, some more serious and rigorous testing here. So we're going to be looking directly at a property of the modified Newtonian dynamics model, which is that acritical should be constant throughout the universe. So how can we test if it's confident or it's constant? We can use an MCMC algorithm to sample from the posterior distribution of acritical and compare the different distributions. See how similar they are. So I actually sampled, though, technically from log acritical because acritical's distribution was quite skewed and it made it difficult to actually see the relationships between the other parameters. So I wanted to use log acritical, but it should be an insignificant difference. I also used log uniform priors because they're uninformative of the scale, which is great because our galaxies vary in size, so we shouldn't assume what size it is and what scale it exists on. And we also know it needs to be greater than 0. And also likewise for acritical. So as you can see, here's the mixing plot, which is quite clean, and the corner plot for NGC 2903. Now, there's clear linear relationships between the mass and the radius, which is good. There's also a very strong linear relationship between the size parameters and the acritical value, which is interesting. Now, when you plot the box plots of all the different posterior distributions, this is what you get. Now remember that we're looking at the distribution of log acritical, so the fact that these medians vary so widely around 0 is quite concerning for MOND and the consistency of acritical. However, we have to consider the fact that these distributions are very, very broad, so it makes it difficult to claim with any substantial oomph that this is the correct conclusion to draw. So let's possibly look at a different method. You can also use cross-validation. Now, I use 1,000 different iterations of picking training and validation sets, and I found the best fit parameters against the training sets, and then calculated the chi-squared against the validation set. Now, each time, each iteration, a different training and validation set was chosen, and this is the 50th iteration for NGC 1003. Now, in each iteration, whichever model has a lower chi-squared gets 1 point added to their score. And by the end, you get this sum of scores and an odds ratio of 1.183 estimated, and it's in favor of dark matter. Again, this is an unsubstantial result, however, it does favor dark matter, and I'm starting to notice a pattern. We're seeing that dark matter is favored on all of these models, but it's not statistically significant yet, and that begs the question, what could possibly be done in order to make these more impressive or meaningful results? And I think that it would really come down to using more galaxies from the Spark data catalog. But the big issue with that is that the computing power required to do these methods is very, very high, and it's expensive methods, computationally expensive methods. So either the methods would need to be optimized or a more powerful computer would have to be used. The other option would be to use data with smaller errors, but I don't think it would create as big of a change as just using a more powerful computer or optimizing the methods. And with that, that's really all I have for you today. we can clearly see that we're moving in the right direction because, as we know, dark matter is a much more favorable model than MOND. But yeah, this is a very interesting statistics problem, and I appreciate you following along. Thank you. Have a good one.